tonight is Professor Ballantyne from the Center for Relativistic Astrophysics, who's going to tell us about supermassive black holes. And I encourage you, after the talk, to come down and ask plenty of questions and satisfy your burning curiosity. Thank you.
All right, thank you. As promised, I'll try to project. So I'm going to talk a lot about supermassive black holes. I'm honored that a lot of my physics colleagues managed, but they're going to be hugely disappointed. I took a lot of the physics out. But I'll try to inject some on the fly as we go. So first, since this is a very general audience, I wanted to just dispel a few rumors, nasty rumors about supermassive black holes. So let's first talk about what you might normally think of a black hole if you've stopped a random person on the street and said, what is a black hole and what does it do? And they might say, well, it's just a cosmic vacuum cleaner. You know, evil cosmic vacuum cleaner that just sucks up anything that's in the past and destroys things and is just terrible, horrible pestilence on the universe. And I really thought that picture would get a laugh. I'm really, really disappointed. I'm off to a terrible start. Oh well, you can only go up from here, right? Once you've hit bottom, you can only go up. So the first thing I have to tell you is that is entirely wrong. Black holes are not evil cosmic vacuum cleaners that suck up things. Certainly, if you got very close to them, it could be very painful and be a very quick and gory death. But if I just magically switch the sun right now and put a black hole and replace the sun with a black hole with the same mass, nothing would happen. All life would be destroyed immediately on Earth because of the lack of sunlight and heat and energy. But other than that, nothing would immediately happen. Our orbits would be the same. Even Mercury wouldn't notice a difference in terms of its orbit. It's only if you get very, very close to a supermassive black hole into this regime of what we call relativistic physics that the weirdness really starts coming into play. So black holes are cool, as I'll explain today, but they're not, these destructive cosmic vacuum cleaners. And if you don't believe me, you can believe this guy. It's false. They're not cosmic vacuum cleaners. All right, so we are improving slowly. All right, so now we've dispelled the public's view of black holes. So what about a physicist's view of black holes? If you ask physicists to draw a picture of a black hole, a lot of them might just describe something that looks like this, which is pretty accurate. It's symmetric. This projector is wrong. Don't just ignore this projector. This projector is accurate. A black hole is spherically symmetric, or in projection, it looks like a circle. It's black because it emits no light, because of its strong gravity. And so this is a pretty accurate picture of a black hole. Now, if you go and take a few more physics courses, especially, I forget what the number is, Relativity, and I asked you what a black hole was, you would write down something like this. So this would be a physics senior's picture of a black hole. We know black holes are really just very strong curvatures in space-time and can be described by this vomitous mess of letters, which is basically called the Schwarzschild metric, and just describes how orbits of things would move in this very curved space-time. And there's certain orbits which are interesting, and we'll talk about those as we go on. I'm not a real physicist, though, but don't tell them. It's a secret. I'm an astrophysicist, so when I think of a black hole, I think of things like this. These are the pictures that come into my head. So the first, on the left-hand side here, is a Hubble Space Telescope picture of a massive nearby galaxy called M87. And sitting in the center of M87, there is a black hole that weighs over 1 billion times that of the sun and is interacting with its environment. And as part of that interaction, it's spewing out these jets of highly relativistic particles that extend thousands of light years across the galaxy and emit radiation that we can detect with our telescopes. So these are black holes that are interacting with their environment and causing radiation and particle acceleration to be dumped into the galaxy on large distances. I also think of diagrams like this. On the y-axis here is a measure of the mass of supermassive black holes that we can measure in nearby galaxies. And on the x-axis, it's basically the velocity of stars that are close to the black hole. So it's a measure of basically the mass of the galaxy. And you can see that massive black holes sit in massive galaxies. In fact, we now know that almost all massive galaxies have in their centers a massive black hole. And explaining why massive black holes sit in massive galaxies is actually quite an interesting problem to investigate. So black holes are not just the theoretical playthings of your lonely physicists sitting in the office making indices dance amongst their equations. So that was a physics joke there. They're now real objects that we can study and interact with their environments. And as an astrophysicist, that's what excites me, is how do supermassive black holes, these very relativistic, compact objects, interact with their environments and affect structures like galaxies and the formation of galaxies. And there's some very interesting physics that happens around black holes that is to study. And that's what I'm going to try to describe in the talk. So here's an outline. I'm going to introduce some of the more jargon about supermassive black holes. So I'm sure it'll lapse into the jargon, and hopefully you'll understand what I mean. I'll talk now about then I'll talk about the center of our own galaxy, which has a supermassive black hole. It's called Sagittarius A star, and is by far and away the most sort of ironclad evidence that these objects are actually real and not just sort of mathematical oddities. And then I'll talk a little bit about supermassive black holes in other galaxies and why studying them it allows us to study very interesting physics. So first, just a quick introduction to supermassive black holes. I'm going to talk about black holes of different masses. The unit of mass we use in astronomy is the mass of the sun, or a solar mass. It's given this symbol here, M, and a little circle with a dot in it. The circle and the dot means sun. So one solar mass is 1.989 times 10 to the 30 kilograms. And when I talk about a supermassive black hole, we're generally talking about objects which have masses greater than 100,000 solar masses. How do these guys actually form? I'm not going to talk about because it's largely unknown. It's a topic of current research, and we have a professor in the department, John Wise, who actually studies this in a lot of detail, trying to form the first supermassive black holes. But they're likely built up through basically a complex interaction of accreting or sucking in material from their surroundings and also merging with other black holes in something called a merger tree, which is sort of schematically just drawn like this. But an individual black hole might have a very different history from any other black hole because it's gone through its own sort of merger and accretion history environment. Aside from mass, black holes can also have an angular momentum or a spin. And we commonly denote how much it's spinning by using this parameter A. And the reason we can use A, which is nice, is because it basically can take any value only between 0 and basically 1. And so it's called the dimensionless spin parameter. So when A is 0, then the black hole is considered non-spinning, and the space-time around it is described by something called the Schwarzschild metric, which you saw a few slides ago. And if A is close to 1, then it's described by different space-time called the Kerr metric, and it's a maximally spinning black hole. And one of the interesting things we want to do as astrophysicists is try to measure space-times around black holes to see if they're actually described by these theoretical descriptions, these metrics. Of course, the spinning black holes are interesting because they can actually spin space-time around it as you get close to the black hole. So that you get some even cooler physics at that stage. So let's talk about the galactic center first. So we sit on sort of the outskirts of a spiral galaxy. There's the sun there on our top-down view of the Milky Way. There's the center of the galaxy. It's about 25,000 light years from us. And for those of you who know your constellations, the center of the Milky Way lies in the constellation Sagittarius. And for those of you who know the constellations, you will realize that's useless information because you can't see Sagittarius from the northern hemisphere. But if any of you ever travel to the southern hemisphere, you go backpacking in Australia or whatever you young people do for fun, you can actually see the center of the galaxy. Of course, when I say you can see the center of the galaxy, I actually mean you can see in the direction, but you actually can't see the center. Because since we sit in the spiral arms of the galaxy, the spiral arms, which are full of dust and gas, they tend to absorb a lot of starlight. So if you actually look towards the center of the galaxy from the southern hemisphere, this is what you see. You see the bulge of the galaxy, which is a bunch of older stars. And then towards the center, you don't see very far because there's a whole bunch of dust in your way. So all you see is basically a silhouette of spiral arms. So that's not very good. It's hard to actually study something when you can't see it. So we can get around this problem, though, by looking at light at different wavelengths. This is in the optical light. This is what you would see with your eye. But dust absorbs optical light really well. It doesn't absorb infrared light very well, or radio light at all. So if we change the way we look, if we change our eyes to infrared eyes or radio eyes, then we can see right through this dust all the way to the galactic center. And so this is what the center of the galaxy looks like in the radio, using radio telescopes. And we see a very rich and exotic region of the galaxy. There's lots of filaments, supernova remnants, places where stars have gone bang. There's lots of pulsars, cores of dead stars. There's lots of gas interacting. And then there's at the very center here, there's what's called a non-thermal radio source, and that's denoted as Sagittarius A star. And that sits right at the dynamical center of the galaxy.
What is the snake?
The snake. Where's the snake?
Just a little bit. That's it.
Right there? Yeah. It's probably just some wiggly bit of radio emitting gas. It's probably the shell of something, some compressed gas. So how can we study the region around the center of the galaxy where we would think a black hole would be? Especially if we want to actually try to measure things like masses. Well, we would have to measure the motions of something going around the center. So we can use our theory of gravity and Kepler's laws and figure out the mass. So the way astronomers do this is by looking in the infrared, so they can mitigate the effects of dust, but also have very good sensitivity and spatial resolution. And so if you look in the infrared, you can, and then use a technology called adaptive optics, which I'll describe in a second, you can actually resolve the stars around this region, Sagittarius A star, very well. And then if you take enough pictures of these over many years, you can actually see these stars move. You can also see monitoring this. This is supposed to be an animation. There you go. I don't know if you saw this. This is a time-lapse movie of Sagittarius A star taken in the infrared. And you can see it burps a little bit. In fact, there's a little bit of a variable infrared and X-ray source there, which shows that the black hole is eating a little bit and producing some radiation. So we can only do this because of this technology that engineers have developed called adaptive optics. And so I'll describe a little bit what adaptive optics is because it's kind of cool. So we put most of our infrared and optical telescopes sit on the ground on a mountaintop and have to look through an atmosphere. Now our atmosphere is full of winds and turbulence, and so even though the radiation, say, from Sagittarius A star at the top of the atmosphere might be very coherent and sort of a nice plain wave, as it traverses this turbulent air in the atmosphere with wind and everything, you get different indices of refraction in different parts of the wavefront. So by the time it actually passes through the air and gets close to the telescope, it's all crinkly and messed up. So when you hit your telescope, you actually don't get a nice, clean, perfect, round image of a star or something. You get a blob, and a time-dependent blob as well. There are things called speckles, and I don't know how well you can see them, but they're this is a time series of different speckles from just looking at a star through the atmosphere. And astronomers call this degradation of the image quality seeing. And so we would talk about, wow, we had 2 arc-second seeing that night, or we had a really good night, it was half arc-second seeing, which means that's how good our image quality was. But what you could do is, since computers are fast enough and engineers are really clever, you could figure out a way of correcting for this distortion in real time. So the way this works is you need a control to sort of monitor the atmospheric turbulence. And so you need what's called a guide star, or a position star. Sometimes you might find a star in your field of view, but sometimes the biggest telescopes have such narrow fields of view that there's only the object you're interested in, and there's not a guide star. So what you do, you make your own by shooting a laser up into space. A freaking laser beam shot from your telescope up into the atmosphere interacts with sodium atoms in the atmosphere and creates a nice spot of light just in your field of view. And then by monitoring that along with your target and using deformable mirrors and computers and feedback and switches and engineering things that I don't understand, you can in real time compensate for the flickering of the atmosphere and remove it from your image. And therefore get a picture that's as good a quality as if you took your telescope and put it in space. Well, a lot cheaper. Because it's really expensive to send a telescope into space. So with adaptive optics systems, you can create these very nice high-resolution images. So we can study the motions of the stars around Sagittarius A star. So here's an example. This is what the image quality goes from off to on in terms of adaptive optics. And I got all these images from a team at UCLA, which uses the Keck telescopes in Hawaii to do all this monitoring. So you can see here in the inner 1 arc-second, you can finally start with adaptive optics resolving a whole bunch of stars. So this is what allows us to do what I'm about to describe and measure orbits of stars close to the black hole. And so using that technology over the course of many years, this group has been able to track out the orbits of stars in the inner regions of our galaxy. Now remember, of course, we don't see the black hole itself, but the black hole has very strong gravity, so the stars orbit the center of gravity and trace out these orbits. And you can see them again, there's just individual numbers. And in particular, this guy with the magenta line, actually forget him, is the yellow guy. That's important because we've been able to actually trace out an entire orbit with him, which is very constraining. Of course, these are in 3 dimensions. While the orbits are coming out at you and going into the screen, but you can actually account for that. And so this is what you would look like if you just put them all down. So we have, what's this, about 10 stars that we've been able to track all the orbits with. And this is very constraining in terms of the mass of what's sitting in the center. And here's the constraints. So this is the enclosed mass within a radius from Sagittarius A star. This is measured in an astronomical unit called parsecs, but 1 parsec is about 3 light years. You can ask me later why it's like that, but it's not important right now. And from measuring the motions of stars and the amount of stars in the area, we can basically find that as you get closer and closer to the center of our own galaxy, the amount of mass you need in order to account for the motions of those stars, and this is high school physics basically, it's just Kepler's laws. There's nothing complicated here in terms of the physics. You're just measuring motions and using F equals ma. You've defined the amount of mass. This is what's known from the stellar cluster at the center of our galaxy. You find as you get closer and closer, you need just a constant point source of mass at the center of about 2 to 3 million solar masses. And the density required of some ball of something you would need in order to make the same motions would be 10 to the 17 solar masses in a cubic parsec, which is just ridiculously large. In fact, that the density required of a group of objects you would need in order to account for these stellar motions rules out almost any possibility than a supermassive black hole, one compact object. Because all these other things here, they would be packed in so tightly that they would just collapse to a black hole anyways, because they would just merge into each other and collapse down. So these constraints have only gotten tighter over the years, and basically we know that in the center of our galaxy there's a massive dark object with about a mass of 2 to 3 million times that of the sun, crammed into a space so small that nothing else other than a black hole can explain it. So that is the best evidence for supermassive black holes. Fortunately, it's hard to do the same experiment in other galaxies, but there's nothing really special about our galaxy in terms of its structure. So I made a little caveat there, which is, how do we know this is really a black hole? All we can say is that it's a massive, very compact, dark object. But is it really a black hole as described by relativity? Well, there's experiments being developed right now to actually try to test that. And the way to test that is that you want to actually measure not just stars moving, close to the object, you want to measure gas falling into the black hole. So you can actually trace out that metric, which tells you how space-time is warped close to the event horizon. And pretty soon we hope to be able to do that, or astronomers will, using a technology called very long baseline interferometry. And the way that works is by combining the signals from telescopes situated all over the world. These are radio telescopes. Again, you have to go to long wavelengths to pass through all the dust in the galaxy, and combine the signals of all these different telescopes. I'll explain why you want to combine them in a second. This combination they're calling the Event Horizon Telescope, which just sounds cool. And these are simulations of what they hope to see. This is a simulation of gas falling into a supermassive black hole. And all these sort of warping, sort of curved features here are predictions from general relativity. So, and the different rows here are actually different spins for the modeled black hole. So this is no spin, this is rapid spin. And so I hope is by trying to make images like this, you can actually measure the metric and see if it's really a black hole described by relativity. So again, I'm going to describe a little bit about the technology we would use or are using to make this experiment. So with radio telescopes, they look like this. They use big dishes. You don't need mirrors because the radio wavelengths are very long. So all you need to do is get some parabola to focus them towards a receiver. But because they have very long wavelengths, we can use this interferometry method to combine the signals. So the way this works is you take antenna 1, say, looking in that direction, and antenna 2, looking in that direction. The incident radio waves come in, and because these guys are situated a little bit apart from one another, antenna 1 and antenna 2 will receive those signals at a slightly different time or at a slightly different phase in the radio wave. And if you know this distance between the telescopes very, very well, then by measuring the time delay between when antenna 1 and antenna 2 made those measurements, you can figure out a way of combining these signals to actually construct an image that would be the same as if you had an antenna the size of D. So you can actually increase your resolution extremely to extreme powers by spacing these telescopes at large distances. So you can see why the Event Horizon Telescope has telescopes all over the world. By combining their signals like this, they will be able to construct an image equal to a telescope the size of the Earth, which would be very hard to build otherwise, right? So it's a very powerful technique. Of course, it requires an immense amount of computer processing. You need to know the distances very well. There's a lot of really, really horrible signal analysis that goes into that, which is why I'm not a radio astronomer. But it's this technique that allows the high angular resolution we'll be able to get to actually hopefully see gas falling right into the black hole at the center of our galaxy. And they're actively taking data now, so hopefully in the next few years we'll be able to test gravity in that very strong regime. I am now going to take a drink, so if you want to ask a question, now's the time. Or you can just let your mind be blown or whatever. Yes, you at the back. Mm. Yes. Yeah. That's an excellent question. I actually don't know how they do it, but it's probably something like that. But I actually don't know the exact details of how they do it.
Would it help to put a telescope on Mars?
Probably, but doesn't sound very cost efficient. Yeah.
I don't know if I saw that picture, the map, but were one of those satellite arrays on the South Pole?
Yeah, there's something called the South Pole Telescope. It's actually a telescope designed to look at the microwave background, the Big Bang baby picture. But it's a radio telescope, and so it can be added to all these other telescopes if the various teams get together and so on. So all you need is just different radio telescopes. And the infrastructure with clocks and so on, and computers to actually do the reconstruction afterwards. All right. Good. So let's now step outside our galaxy, because there's billions of other galaxies and they're all interesting to study. And as I said, basically we now know that pretty much any massive galaxy has its own supermassive black hole sitting at the center. One of the interesting things about Sagittarius A star is that it's what's considered a weak black hole. It's not really actively sucking in material. It does these little burps that you see, but it's actually, they're very, very faint, which makes it nice to study in terms of peering down towards its, to its location, so you can study the motions of stars. But you don't really get the fireworks that we sometimes see from other supermassive black holes, like these jets. So there's a class of supermassive black holes that are sucking in material rapidly. And those are called accreting black holes, or AGNs, or quasars. And they shine very brightly in the centers of their galaxies. Of course, it's not the black hole that shines, it's the material falling into the black hole that shines. And because they can radiate so brightly, you can observe them to great distances, and they're very good for studying black hole populations over the age of the universe, for example. So, like material going down your bathtub, material falling onto the black hole will turn into a disk and rotate. It has angular momentum, so it has to get rid of that angular momentum before it can fall down the black hole. And so it rotates in a disk, and that disk is very good at converting gravitational potential energy into thermal energy, which basically heat, which the disk can therefore radiate away. And we see this disk shining to megaparsecs away. How the angular momentum transport actually works is very interesting and very complicated physics. It was only figured out a couple of decades ago. It's due to what's magnetohydrodynamical turbulence caused by the magnetorotational instability, which probably one person in the audience might know about. What it is, though, is it's just, I don't know if this guy will play on its own, but basically magnetic fields in the gas cause friction, and the gas can transport angular momentum and fall into the black hole.
Today, this is a fact?
Yes. Well, it's been a fact in the sense that it's been verified by computers. People are trying to verify it in a lab. Problem is the Reynolds numbers of these astrophysical flows are really ridiculously high, so it's hard to actually do this in a lab. But it works pretty much any time you try to set it up in a computer. And so this is a computer simulation of that accreting gas onto a black hole. So there's some interesting physics going on there, which is interesting to study. So now let's go back to this disk around a black hole and go to the idea of the different metrics. Now, if you study the metrics and with the disk around it, you find that the inner edge of that disk depends almost entirely on one parameter, the spin of the black hole. The inner edge of a Schwarzschild non-spinning black hole is basically 6 in those units. But for a Kerr black hole, these maximally spinning black holes, the inner edge moves to about 1 GM over c squared. And just to give you a sense, GM over c squared is 0.1 astronomical unit, or a tenth of the Earth-Sun distance for a black hole of 10 to the 7 solar masses. So that's a pretty small distance, astronomically speaking. So if you could somehow measure something that would give you the inner radius of this accretion disk, you could get a handle or measurement on the spin of black holes, even though they're a gazillion miles away from you. And one way we can do this is by looking at the X-rays emitted from these black holes, these AGNs. All these AGNs produce a ton of X-ray emission. Basically because there's just so much energy available, it's easy to tap into to accelerate electrons to emit X-ray energies. And the X-rays come from very, very close to the black hole. And we know this because they vary extremely rapidly. So this is a plot of the X-ray light as a function of time for one particular AGN. It's called a light curve. And you can see it flickers up and down. And it also has these big jumps and dips. And this peak-to-peak transition here is 2,500 seconds, which is a light crossing time of 5 astronomical units. So that's the distance between the Sun and Jupiter. So we're seeing variations in an X-ray emitting region smaller than the solar system and around a black hole that's a bazillion miles away. That's the technical term, bazillion, right? So we can use these X-rays to hopefully study these inner regions around the black hole. Incidentally, you might wonder, where do the X-rays come from? It comes from the accretion power, but it's interesting how we think we convert it into X-rays. A very close analogy we use is to look at the sun. Now the sun obviously shines a lot in visible light, but it also has what's called a corona around it. That's what you see around the sun during a solar eclipse. It's called the solar corona. It's very low density gas, but very hot. And in fact, it emits in X-rays. And how does it get that gas so hot that it emits in X-rays? We think it's due to, basically heat dumped into the corona through magnetic fields again. You can see this picture of the solar system with these magnetic sort of curtains and plasma flowing around the magnetic fields. Here's another movie taken by the TRACE satellite of the, where are you? There you are. The solar corona. And you can see all these wonderful magnetic structures in plasma being blown out. And then you get events called reconnection, which can convert the magnetic energy into thermal energy. And if you ever want to spend a lazy afternoon, find the TRACE website and just stare at those movies because they're beautiful pictures of the sun in action. And we think the same kind of thing is going on in accretion disks around a black hole. That this would be the accretion disk, and the magnetic fields, which we know cause the angular momentum transport, also transport plasma up into a corona and emit X-rays. One other sort of side note for those of you technologically minded, it's also very interesting of how do you actually observe X-rays with a telescope. You can't actually put a mirror down at the bottom of a tube and you hope it detects X-rays because the X-rays just get absorbed. They're too energetic. They don't bounce back like optical or infrared photons. But you can do it by what's called grazing incidence optics. You take your mirrors and you put them on the side, and it turns out if you have an angle of incidence very close to 90 degrees, you can actually get a small amount of deflection, enough to focus the X-rays down onto a focal plane. And there you can put your camera, your CCD type optics and sensors to make X-ray images. And how do you actually make a bigger mirror? One of the lovely things about having the mirror on the side is you don't just make them bigger, you just add more of them. You nest them together. So you just put these concentric mirrors together and you can get more and more collecting area. It's a really wonderful design. Requires a fairly long focal length, but you can do it and launch these guys into space. Anyways, so back to the AGNs. We know we have X-ray emitting blobs near a black hole because of their variability. We think they appear above the accretion disk because of the corona. So one of the interesting things then is that they'll actually have an X-ray flare shining onto the accretion disk. And this, the accretion disk will reprocess this X-ray light and reflect it back towards us. And we'll see a combination of both power law, the primary X-ray emission and the reflected emission. The most prominent feature we see in this reflected emission is an emission line of iron at 6.4 keV. And it's interesting to think about what an emission line, which is normally just at one energy, will look like if it's coming from a spinning disk close to a relativistic object. So this steps you through it. So if you just had a line from a spinning disk and you were in Newtonian physics, then you get, just from the Doppler effect, a red shifted part from the side going away from you and a blue shifted part from the side going towards you. So you get this double peak profile. So instead of one spike, you get split into two spikes from the rotation. But if you're close to a black hole, that rotation is actually 10 to 20% of the speed of light. So you have to take into account special relativistic effects. And what the two special relativistic effects that kick in is what's called beaming, which is the side coming towards you is enhanced in brightness, and the side going away from you is diminished in brightness. So your two-horn profile suddenly becomes very asymmetric. You get a much bigger spike on the high frequency blue side than on the red side. You also get a slight shift to lower energies or lower frequencies due to what's called the transverse Doppler shift, which is basically moving clocks run slow. And then finally, since you're deep in this potential well caused by the black hole, you get what's called a gravitational redshift. All the photons lose energy as they climb out of the well. So the whole thing moves even further to lower energies. So if you add everything up and you assume there's some annulus emitting, you predict this sort of asymmetric profile. Cool thing about this profile is that if that line is being emitted all the way down to the inner edge of the disk, then that will give you different amounts of gravitational redshift. So a Schwarzschild non-spinning black hole, remember, has an innermost stable orbit of 6 gm over c squared. So that gives you only a certain amount of redshift that you can get. And that cuts the line off down here. For a maximally spinning black hole, the disk can go much further in. If the line's being emitted all the way down, you can get much more gravitational redshift, so the whole line skews even to lower energy. So if you can measure these lines precisely with an X-ray telescope and measure where these things cut off, then you can actually measure the spins of black holes. Cool. And this has been done. You can do this. This is an actual real data with a model fit to it that measures the spins of black holes using this emission, fitting the emission line. So astrophysicists are actively measuring the spins of black holes, and we're finding that a lot of them spin rapidly. Some not so much, but most of them seem to be explained by the Kerr metric. And that in turn tells us about how the black holes were formed, because in order to spin a black hole up, you need to basically give it angular momentum, which means it has to accrete through a disk for a long time. So that tells us a little bit about its history as well. So that's, I think, pretty cool. So now on to the final topic. Excellent. About the relationship between black holes and galaxies as a whole. So I told you that, because we know that massive black holes sit in massive galaxies, they actually seem to suggest that there's a common evolution of the two objects. And you can sort of realize this if you think about it, because as I said at the beginning, black holes are not cosmic vacuum cleaners. You have to get really close to a black hole even to even know that it's there. And galaxies are ginormous compared to the size of a black hole. So all the stars in these galaxies don't know there's a black hole, let alone know what its mass is. So how come we end up with such a nice relationship between the mass of the black hole and the mass of the galaxy? Because the stars in the galaxy have no idea. So that sort of indicates to us that as the galaxy is being formed and the black hole is being formed, that there's some sort of symbiotic communication processes going on that set up this relationship. And one way to sort of study this that I've been pursuing is studying what's called the cosmic X-ray background, which is basically the integrated light in X-rays of all the accreting black holes in the entire history of the universe. And sort of basically the sky glows in different wavelengths, and this is sort of the spectrum of all those backgrounds. This is the famous microwave background, or the baby picture of the universe, and down here is the X-ray background. But even though the X-ray background's like 5 orders of magnitude weaker, it was actually discovered first before the microwave background, back in the 1960s. Went back when people stuck X-ray detectors on the top of rockets and shot them into the sky and then ran after them and opened it up and go, did I find anything? And the first guy who did this found 2 things. But neither of them he was actually looking for. He was looking for the moon and he missed it, which is weird because it's right there, right? But it turns out the moon is very dim in X-rays. Incidentally, that is a picture of the moon in X-rays. The moon doesn't emit X-rays, it's dead cold, right? But it actually emits X-rays in scattering because the solar wind chucks out protons and so on, and those hit the moon regolith and stop, and that produces a small burst of X-rays. So there you learned something today. So that's what the moon looks like in X-rays, but Giacconi didn't see that. He saw SCO X1, which is the brightest X-ray source in the sky, and he also discovered that the sky was glowing in X-rays in every direction, which is now known as the X-ray background. And that's what it looks like. Its spectral shape as a function of energy. It's kind of boring, but for many years, the origin of that was a mystery. But we now know that the X-ray background is, as I said, the integrated emission of all the accreting black holes in the history of the universe. So if you take an X-ray telescope like Chandra and stare at a small patch of sky for 4 million seconds, this is the kind of image you get. It's kind of boring compared to a Hubble image, but every single dot you see there is a growing black hole in the middle of a galaxy. And if you add up all this light, you make up the X-ray background. So studying the populations of these guys and the galaxies they sit in will hopefully shed a lot of light onto how we get that black hole galaxy relationship. So yeah, every dot in that picture, there's something that looks like this. It turns out a lot of the black holes that are in galaxies have a lot of gas and dust around them. It's not surprising. You need gas and dust to fall into a black hole in order to fuel it. So there's a lot of sort of junk around there that blocks our view. So in order to actually study these X-ray sources in a great bit of detail, you need to study the hardest X-rays you can. The highest energy X-rays have a better chance of penetrating all that gas and junk and study it. And so to actually make it through to our telescope. So one of the things I've been involved in the last few years is NASA's latest X-ray telescope called NuSTAR. It's a project led out of Caltech. And it was launched in June 2012. And it's the first X-ray telescope to actually focus X-rays in the very highest energies. And note how it has this really long boom here. It wasn't launched like that. It was launched all folded up. And this movie sort of gives you an animation of how it actually was deployed. Remember I told you that to focus X-rays you need grazing incidence optics. So you put the mirrors on the side and they deflect a little bit, and then you put your detector way down there. So the highest energy X-rays, you need the largest focal length. So you need to have this really long path. Very hard to launch something like that. So the way it was done is you launch it compact, and then you put squirrels in the center, and then you flash like lights, and they start running, and then the boom starts. It was a small mission. You have to make budget decisions, right? So you put I'm kidding about the squirrels. They were hamsters. So then the boom slowly comes out, and it takes several minutes, and people on Earth have heart attacks hoping it doesn't break because there's no fixing it. But it all worked, and we've been able to use it for the last 2 years remarkably. And just to give you an idea of what it can do, this was NuSTAR's what's called first light image. So prior to NuSTAR, if you wanted to look at an X-ray source, it kind of looked like that, like a blob. And now it looks like a nice dot. So it's like adaptive optics for X-rays, just the huge increase in resolution and sensitivity. And so what we've been able to do is take this new capability and stare at those patches that Chandra was able to discover. And this is a Chandra image in the background. But Chandra only looks at low energy X-rays, so I can't see the really deeply embedded, heavily obscured black holes and those galaxies. But with NuSTAR, we can find them. And so this is the purple here are the NuSTAR discoveries on the Chandra image. So we're able to actually discover new sources that haven't previously existed, which will, by studying their properties and galaxies, will hopefully cobble together an idea of how black holes and galaxies grow. And basically here are all so the gray part are all the pre-NuSTAR type of black holes. They're all really nearby. NuSTAR's basically blown this open by a factor of 10. We're studying populations that haven't been detected at all yet. So this is my summary, but basically the take-home point is black holes are a completely essential part of modern astrophysics. They're not science fiction anymore. They're not just theoretical mathematical oddities. They're real things that affect the universe. They affect how galaxies are grown. And because we live in a galaxy, they indirectly affect how we came to be here. So they're important to study and understand. Black hole environments are also extreme, so they're making very lovely laboratories to study physics in ways that you cannot study here on the ground. I'm sure my colleagues would love to put a black hole in a lab and study it, but it's just probably kind of breaks safety protocols somewhere along the line, so it's much better to study them up there when they're not going to do us any harm. So, and as I said, there's very interesting extreme sort of magnetic and thermal and radiation physics going on. So they're wonderful to study from a basic physics perspective. So the galactic center gives us the up-close view of a black hole. Even though it's kind of boring, it allows us to measure its properties extremely precisely. And hopefully we'll be able to actually watch material drip into it in the next few years. And the really rapidly growing black holes in our outside in the universe allow us to study the physics of black holes, as well as study the physics of the interaction between black holes and galaxies. So I'll stop there. Thank you for your attention.
We have time for questions. Any questions for our speaker?
Is there a minimum mass of a black hole?
Astrophysically,
Anyway, because we have heard in the past about the possibility of micro black holes from accelerators on Earth, but astrophysically, is there
so the two mechanisms we know that definitely make black holes, the lowest mass ones are basically formed by the collapse of massive stars. And those typically make black holes on the order of 10 solar masses. It's hard to come up with an astrophysical model that will produce lower ones. There are the idea,
spin doesn't affect it?
probably only a little bit. There is the idea of what's called primordial black holes that were formed in the Big Bang. Of course, the other thing to keep in mind is if Hawking radiation exists, then black holes evaporate over long time scales, but it goes as the inverse mass. So the smallest black holes evaporate the fastest. So really, really tiny black holes will have already evaporated and been gone. And so the fact that we don't see any is sort of consistent with that idea. But there's not been any sort of, I think, proof that they haven't, they're not there. People have sort of constrained various areas of parameter space, and I think it's pretty much all closed in at this point.
Any questions for our speaker?
So what's the next observations going to be that we think about? If we say you showed that like most of from the earlier data that a lot of the black holes that we see right now are more of the curve, right? And
Right.
that gives us some hint about the mechanism. I'm just trying to understand what the alternative hypotheses are still of how the galaxy and the black hole may be
Right.
biotically evolving over time.
Right. So a competing theory is something what's called chaotic accretion, which is over the growth of the black hole, it's been fed sort of from random directions. And so the angular momentum it's given is random. And so sort of on average, what will happen is that will spin it down. And you'll end up with more low spinning black holes than high spinning. We can't really test those things yet because these observations have not been done with sort of like a clean selection, a well-defined sample. It turns out that you need basically really bright objects to do this kind of work. And that is not a well-defined sample, just the brightest things. Often the brightest, most intense things are the outliers because those are the ones you see easiest. So I think as the next generations of telescopes come online and we're able to do more sort of surveys of these type of things, and we'll be able to come out with a nice statistically well-defined sample, then we'll be able to start sort of hopefully testing those theories and maybe even looking at populations of black holes at different epochs. So as we go further back in distance, of course, we see the universe younger and younger. So it would be interesting, of course, to trace the evolution directly like that. But that's going to require much more sensitive instruments than what we have now.
There's some thought that there's different kinds of black holes and different kinds of galaxies.
Yeah, I think people sort of would think that you can't just like you can't study 5 random individuals and learn a lot about the human race from 5 people because everyone's history and makeup is different. We need to sort of study well-defined samples. But still, individual black holes might have various different histories. We just need to get our statistics.
Last question?
Yep.
So you said that you're going to try to use black holes as like extreme laboratory, right?
Right.
So what are some of the like the physics, like some of the theories that you would like to like prove using that?
Well, the first would be gravity, because although gravity and relativity has been tested in what's called the weak field regime, it's not really well tested in the strong field regime, where it's close to these very compact objects. And ideally you want like a test particle around one of these things so you can actually trace out the space-time and see if it is described by these solutions. So that's one thing. And then the other is just sort of the energy densities in terms of gases and radiation and magnetic fields are all really intense here. The gas flows are very turbulent and very magnetic. So there's just sort of very interesting dynamical physics that goes on around these systems. That's just very hard to probe experimentally down here.
All right, next week we have Professor Fenton, who will be talking on the physics of Frankenstein. And being as close to Halloween as we are, he promises to dress up in costume. Let's thank our speaker one more time.